for section 4.5, what we're actually going to be studying at and looking at a few examples is one of the fundamental concepts that we see in physics, and that is the the conservation of energy, which tells us that energy cannot be created or destroyed it can only change from one form to the other. And that really helps us analyze some different types of problems that might arise in physics. We notice, or we know, that the total initial energy will be equal to the final total energy. And both these, remember, are measured in joules. And for the time being, what we know is that the total mechanical energy is merely split up right now between our kinetic energy and our gravitational potential energy initially, and at the end, kinetic energy at the end, and our gravitational potential energy at the end. So therefore, this tells us that EKI added with EGI will be equal to EKF plus EGF. And this is where EKI is representing our initial kinetic energy. EGI is our initial gravitational potential energy. EKF is our final kinetic energy. And EGF is our final gravitational potential energy. And knowing all this can help us determine or calculate either the final speed, initial speed, maximum height, etc. And that's what we're going to do through our two examples, is to look at a couple of different scenarios that arise. In example 1, we have a 52 kilogram skier, which tells us our mass of the skier is 52 kilograms, and has slid to the top of a 40.0 meter high hill at a speed of 2.00 meters per second, and then continues down this frictionless surface. So that means we know that HI is 40.0 meters and VI is 2.00 meters per second. We can determine the skier's total mechanical energy at the top of the hill. And that total mechanical energy initially is equal to EKI plus EGI. So that will be 1/2 mVI squared plus mghi. And we can make simple substitutions now to determine the skier's total mechanical energy. So that will be 1/2 52 2.00 squared plus 52 times 9.81 with my initial height of 40.0. And we merely take our calculator now, and we can very easily solve for our initial energy. So that will be 0.5 with 52 times 2 squared plus 52 times 9.81 with 40 multiplied all together. And there's our total mechanical energy of 20,508.8. And let us analyze significant digits now. 2 significant digits, 3 significant digits, 3 significant digits. That tells us that our total mechanical energy initially will be 21,000 joules. And this really helps us calculate the skier's speed at a height of 25.0 meters per second. Because we still have that the mass is 52 kilograms, we still have our second height, which will be 25.0 meters. We know that the initial mechanical energy is 20,508.8 joules. Notice how I use the more accurate answer for our calculations, and we need to calculate what the final speed will be at the very end. So we know that our initial mechanical energy will be equal to the kinetic energy at the end, along with our gravitational potential energy at the end. And it merely becomes a case now where use of algebra will help us figure out what our final speed would be. So first thing that we must do is multiply by 2 to get rid of that 1/2. So 2ETI is equal to mvf squared plus 2mg and our final height. Let's bring this term over to the other side to solve for vf squared. So we have 2ETI minus 2mghf is mvf squared. Solving for our final speed, we must divide both sides of the equation by m. So vf squared is 2ETI minus 2mghf all over m. And because of this square root, let's take the square root. And let us see, when we substitute in values, what we get as our final solution. So this will be the square root of 2 multiplied with 20,508.8 minus 2 times that 52 kilograms, 9.81, and a height of 25 meters. And that will be all over the skier's mass of 52. Plugging this into our calculator, let us observe or see what we actually get. So I have 2 times 20,508.8 minus 2 times 52 multiplied by 9.81 times 25. All of that must be divided by 52. And let's take the square root of 298.3, 17.27. And we look in the question yet again, we need 2 significant digits, so our final answer, at 25 meters height, the final speed of that skier will be 17 meters per second. Which does, in fact, make some sense. Because we know that at the top of the hill, which was 40 meters high, going down the hill, we have a maximum gravitational potential energy at the top and our minimum kinetic energy at the bottom. And as we get to the bottom, we have a maximum kinetic energy and a lower gravitational potential energy, which causes our object to speed up as they go down the hill. Which we'll see an example of something like that coming up in example number 2. In example 2, we have a ball that has a mass of 25 kilograms, and that mass, or that ball, is thrown vertically upwards from a roof of a building that is 18 meters high. So that tells us that our initial height is 18 meters, with an initial speed of 16 meters per second. It's thrown vertically upwards to a maximum height, and then it will eventually come back down again. We must realize that right here, our gravitational potential energy is maxed out. And at that point where our gravitational potential energy is our maximum, our kinetic energy, so this will be our final kinetic energy, will in fact be equal to 0. So calculations-wise, we know that VI is 16 meters per second. We know that HI is 18.0 meters. We know that because our final kinetic energy is 0, that our final velocity must be 0 meters per second. So let us calculate what our maximum height would be of this rock from the building. So ETI is equal to ETF I like how I'm switching I's and F's there. Let's keep the I's on the left-hand side. 1/2 mvf squared plus mghf. And due to the fact that vf is 0, this term here completely disappears. And we're looking to solve for what hi would be. So mghi will be equal to, and this will be 2 mghi because we must get rid of this 1/2, will be equal to 2 mghf minus mvi squared. So to solve for this guy here, we will divide both sides of the equal sign. Let's see, by 2 mg. That solves for my hi. And what you will notice is I just completely started this out wrong. So, my apologies, because we're not solving for hi. Let me scratch this out. I got on a spiel, and then I completely forgot what I'm looking to solve for. We're looking to solve for hf, my maximum height. My apologies. So we have 1/2 mvi squared plus mghi is equal to mghf. We look to solve for hf. My apologies here. Ignore all that. That's a 2-minute spiel that unfortunately you just went through, so please forgive me there. Solve for hf. Let's divide everything by mg. So what does that give us? We have mvi squared plus mghi all over mg, 2mg. We can cancel out the m's because they're in every single term, and that will tell us what our maximum height will be. So, maximum height, vi squared plus mghi all over 2g. I can't cancel out the g because our vi squared doesn't have a gravitational acceleration with it. So, 16 squared plus 0.25, 9.81 times 18 all over 2 times 9.81. And we can calculate what our maximum height is going to be. So, that will be 16 squared and you'll see that we get 15.2979. So therefore, our maximum height in relation to the building would be 15 meters high. So therefore, maximum height of this rock in relation to the earth, or into the ground, will be 18 meters plus 15 meters, which will be 33 meters altogether, is my maximum height of this ball in relation to the ground, and the building, it would be 15 meters high. Please do forgive me yet again for that one little mess up there, and I hope that you see that we can easily calculate HF with our conservation of energy.